In this video for Advanced Chemistry 30S, we'll take a look at average atomic masses, how to calculate them using isotope abundances, how to interpret simple mass spectra, and how to find abundances if we're given the average atomic mass and isotope masses. So we'll look at some problem solving involving isotopes here. A mass spectrum is produced by a mass spectrometer, and the simplest type of mass spectrum is shown here. This is one for the element boron. So a sample of boron was injected into the instrument, vaporized, ionized, and then flung through a magnetic field. A detector shows these two peaks for boron. One of them has a relative abundance. That's not quite the same thing as a percent abundance, but a relative abundance of 100, while there's another peak here with a relative abundance of 23. The x-axis shows m over z, which is a mass to charge ratio. We're going to assume that each of the boron atoms in the sample, when they were ionized, resulted in a charge of +1. If their charges were +1, then the mass to charge ratio would be the same as just the mass. So these m over z values can be thought of as masses. Further, we're going to assume that since every proton and neutron has a mass of about 1 AMU, then this mass to charge ratio can be thought of as approximately the same thing as a mass number. Okay, they're not exactly the same idea, but with those assumptions, we can make that approximation. So the first statement says that the graph shows that there are two isotopes of boron. Why is that? How do we come to that conclusion? Well, because boron is an atomic substance made of just atoms of boron, so there's no molecules present, the fact that there are two peaks in the spectrum means that there were two isotopes of boron. Okay? Now, if it were a molecular substance, if it were something like B2 or B3, then the number of peaks would be more complicated to interpret. But for just boron, atomic boron, two peaks means there must be two isotopes. What is the percent abundance of the two isotopes? Well, normally in class when we talked about the abundances, we talked about the natural abundance or the percent abundance of each isotope. Clearly that's what these numbers cannot be the same thing. Otherwise we'd have 100% of one isotope and then another 23% of another one. That doesn't make sense. These are not percent abundances, they're relative abundances. So think of this as meaning in the sample there were 100 atoms of boron in this peak for every 23 atoms in this peak. That's how you should interpret that. So the percent abundance, if there's 100 atoms in one peak for every 23 in another peak, there would have been 123 atoms total between the two peaks. So we can say the percent abundance of the lighter boron isotope, so the first peak in the spectrum, would be 23 out of the total number of atoms, which was 123, the sum of those two numbers, times 100. And that's going to give us a percent abundance of 18.7 or 19% if you prefer. We could do the same thing for the heavier isotope, or we could simply say because there are two isotopes, 100% minus 18.7% leaves us with an abundance of 81.3% for the heavier isotope. Okay? So there we've got the relative abundances from the graph converted to percent abundances in this simple way. What were the mass numbers of the two isotopes of boron? Well, looking at the graph closely, we can see that the first peak is showing up at a number 10 on the x-axis, and as we said earlier, we're going to assume that that ratio, mass to charge ratio, is essentially the same as a mass number because the atoms will have charges of +1, and we're going to assume that every proton and neutron's mass is 1 AMU. So therefore, boron 10 would be one isotope, and the other isotope would be boron 11. Boron 10's abundance would be 18.7%, while boron 11's abundance is 81.3%. So 18.7% of all boron atoms are boron 10, 81.3% of all boron atoms are boron 11. So there's an interpretation of a simple mass spectrum for an atom and its isotopes, for an element and its isotopes. In this next question, we're going to take a slightly different tack. We're going to become a little bit more mathematical. We've got a table showing 3 isotopes of magnesium. And for each isotope, we're told the exact atomic mass measured in atomic mass units. Very precise. Look at those number of significant digits is very large here. And we're told the percentage abundance for each isotope as well. Okay, here are the 3 isotopes, magnesium 24, 25, and 26. Based on that information, we're going to calculate the average atomic mass for magnesium. If you know how to do this, then pause the video, get a piece of paper and a calculator, try it yourself, but don't just try to get the answer, try to show your work in a way that would get full points on a test. So we're going to calculate the average atomic mass. To do that, we're simply going to do a weighted average calculation. So we take the abundance of the first isotope, 78.99%, and we'll convert it back to a decimal by dividing by 100. Now some people do that in their head and just write 0.7899. That's fine, but I've seen people make silly mistakes with the decimal when they do that, so this is a slightly better way to do it to avoid those kind of mistakes. So take the abundance, convert it back to a decimal, and then multiply that by its mass, so 23.985042 AMUs. Okay, so that's the first isotope done. Plus weighted average, so 10%, 10.00 converted back to a decimal over 100, times its atomic mass, so the second isotope, 24.985837 AMUs, plus, and we would just continue this until we run out of isotopes. We've got one more, so plus 11.01% of its atomic mass, 25.982593 AMUs. All right, now we'll grab a calculator and we will do the arithmetic on there. I've already done that, so I'm just going to copy from an earlier page. When we multiply numbers like this, we remember there's a rule that says that the answer of a multiplication has to have the same number of significant digits as the number in the multiplication that had the fewest. So since 78.99 has 4 digits, significant digits, and the mass had many more than that, we're going to round off this answer to just 4 significant digits. Remember that 100 in a percent is an exact number. It's not a measurement, so we wouldn't round off to 3 sig figs based on that, because this number is pure. It's considered to have infinite significant digits. We could say 100.0000 forever, because it's exactly 100%. So equals, multiplying these and keeping 4 digits in our answer, we get 18.95 AMUs, plus multiplying here and keeping 4 digits again, 10.00, we get 2.499, 4 significant digits, plus, again multiplying here, keeping 4 significant digits, we get 2.861 AMUs. And now we're going to add these 3 numbers together, and when we add or subtract, there's a different rule for rounding off the answer. The rule now says round off your answer based on the lowest number of decimal places in the numbers being added or subtracted. So 2 decimal places are in the first number, 3 decimals are in the next 2 numbers. So when we add these 3 together, we're going to round off the answer to just 2 decimal places. We grab a calculator and add them up, and the calculator says 24.31, which is 2 decimal places, so we're good. 24.31 AMUs is the average atomic mass for magnesium. You can check that because average atomic masses are found on the periodic table. So if you looked up magnesium there, you should see 24.31 as its average mass. Alright, this next question is going to be a little bit more complicated. We're going back to boron that we looked at in the first question, and we're going to see if we could work backwards now, and this time without the help of the mass spectrum, but with some numbers that are a little bit more precise. So again, we know there's 2 isotopes of boron, boron 10 and boron 11, and now we know exactly what their atomic masses are. Boron 10, 10.0129 AMUs, and boron 11, 11.0093 AMUs. We're also told the average atomic mass of boron, 10.812 AMU, so that should match what's on a periodic table. Based on this information, can we calculate what the abundances are for each isotope? Now remember, we did this at the start here of the video. We saw the mass spectrum for boron, and in that spectrum we saw that the percentages were 18.7 and 81.3. So we'll now see if we can get those numbers in a different way by calculation. So if you know how to do this, pause the video, try it yourself, and again, focus on showing your work, not just getting an answer. So what I'm going to do, because we have 2 unknowns here, we have the abundance for each isotope, I want to start by identifying my variables. Make sure you do this. We want to let X be the percent, well, rather than percent, I'll just say the abundance of boron 10. And I'm going to make it very clear here in decimal form. In other words, if the percent abundance were 10%, then my X would be 0.1 in this way of interpretation. I'm going to let Y be the abundance of boron 11, also in decimal form. All right? Now, based on those 2 variables, let's write 2 equations. We have 2 variables. Our mathematics tells us we need 2 different equations to solve for this. The first equation is going to be our weighted average that we just did. We know the average mass, so 10.812, the average mass of the boron, has to equal the isotope's mass for boron 10, so 10.0129, times its abundance, X. Now I don't need to divide by 100 here because we said earlier it was going to be in decimal form already. Plus the other isotope's mass, 11.0093, times its abundance, Y. Now I hope you can see that equation and think about what we just did a moment ago for magnesium and see the exact same idea. Okay? Here we divided by 100 because the abundances were in percentage form. If we were expressing these in decimal form, then we would have said the mass times 0.7899, which is what we're doing here, the mass times X plus the mass times Y. So there's one equation, but it has 2 variables. We're going to need another equation. Well, since there's only 2 isotopes, X and Y, are their abundances, we should be able to add those abundances together, just X plus Y, and those should add up to 100%, right? There's 80% of one isotope, there'd have to be 20% of the other. So the isotope abundances here have to add up to 100%. However, because we expressed the abundances in decimal form, 100% would be 1, and exactly 1. So there we have it, our 2 equations with 2 unknowns. The first equation comes from average atomic mass, or the weighted average if you prefer. The second equation is that the abundances add to 100%. So those are the two ideas that we used. So now the chemistry is done, we just got to use some math now. I'm going to look at these two equations, and some people want to use substitution to solve it. I'm going to use elimination. If you want to use matrices or graphing, there's several ways to approach this, but I'm going to use elimination. So I'm going to take my second equation, and I'm going to multiply by, which one of these do I want to eliminate? I'll eliminate the x. It doesn't really matter, so I'll multiply by 10.0129. So that's going to give me 10.0129 equals 10.0129x plus 10.0129y. The first equation, I'm not going to do anything with at all, so I'll just recopy it. 10.812 is 10.0129x plus 11.0093y. And now I'm going to subtract the two equations. I could subtract the top one minus the bottom one, but I can see that's going to give me a negative answer here, and that's fine. You could do that, no problem. But I'm going to subtract the other way around. I'll subtract the second equation minus the first equation to give me positive numbers. So 10.812 minus 10.0129, when subtracting, we keep the smaller number of decimal places, so this is going to be 0.799 equals, this cancels when we subtract, that's eliminated, and subtracting here, 11.0093 minus 10.0129, we get 0.99, we can keep 4 decimals there, 9964y. And now we're going to divide both sides by 0.9964, and we get that y is equal to 0.799 over 0.9964, 0.799 divided by 0.9964, we get 80 with 3 digits, 80.2, 0.802. That's what the calculator says. If we convert that to a percentage by multiplying by 100, 80.2%. And Y was the abundance, looking back up here, of boron 11. So that is the abundance of boron 11. Now, to find the other abundance, we can go solve for X now if we want, or because there's only the two isotopes, we can say therefore X was equal to 1 minus 0.802, which is going to be 0.198, which means multiplying by 100 to convert to a percentage, we get 19.8% boron 10. And hopefully those percentages are similar to what we had earlier. They're not exactly the same, but they're pretty close to the abundances we saw earlier in the mass spectrum. Okay? Not exactly the same, and I'm not sure why they're not exactly the same. I'm going to assume that these numbers, because they were more significant digits, that these are probably the more accurate numbers. Okay? Alright, so there's a slightly harder algebraic problem using elimination or substitution. Here's another question, very similar to the last. Pause the video and try this one yourself. So we're looking at the same kind of question. Gallium-69, here's its mass. Gallium-71, here's its mass. And these are the only two isotopes of gallium. And we're told its average atomic mass. We want to know the abundance. So this is exactly the same kind of question. So let's solve it a little bit faster. Let X be the abundance of gallium-69 decimal form. Let Y be the abundance of gallium-71 in decimal form. Okay? Then one equation we could write would be that 69.723, the average atomic mass, is equal to 68.9256, the mass of gallium-69, times its abundance, X, plus 70.9247 times its abundance, Y. There's my average atomic mass equation for gallium. The second equation will say that 1 is equal to X plus Y. The two abundances add up to 100%, or 1 in decimal form. Now let's solve this. This time I'll use substitution. So we'll say here that X is equal to 1 minus Y. A different pen. X is equal to 1 minus Y. And therefore, coming back to our first equation, 69.723 would be equal to 68.9256 times, instead of X, we'll say 1 minus Y, plus 70.9247. All right, multiplying through these brackets, we get 68.9256 minus 68.9256Y, multiplying through like that, plus oops, I forgot a Y over here, didn't I? Plus 70.9247Y. And now combining the Y's, and I'll move this constant over here, and I'll combine these Y's, we get 69.723, take away 68.9256, keeping 3 decimal places there when we're subtracting, we get 0.797, and over here we have negative 68.9256 plus 70.9247. We get 1.999, and we can keep 4 decimal places there, rather, 1.9991Y. Dividing both sides by the coefficient of Y, we'd get that Y is equal to 0.399, or 39.9% is the abundance of gallium-71. Okay, there's the abundance of gallium-71. Now we can get the abundance of gallium-69 by simply multiplying or subtracting from 100. So 100 minus 39.9 is equal to 60.1%. So there's the abundance of gallium-69 and the abundance of gallium-71. All right, the last question we'll look at is a little bit more difficult conceptually, and it's a little bit more open-ended of a question. We're shown here the mass spectrum for bromine. But notice it's not bromine, atomic bromine, Br, it's bromine, molecular bromine, Br2. So the particles that went through the mass spectrum here, the spectrometer, weren't bromine atoms, they were bromine molecules. Okay, now the mass spectrum gives us 3 peaks. We can see it here, 3 peaks. One of those peaks is at 158, one's at 160, and one's at 162, and the ratios of their heights are 1 to 2 to 1. In other words, the first and third peak are almost the same, and the middle peak is double those two. For more precise numbers, we have this table. The AMU masses of AMUs were 157.84, so that's a 158 peak. 159.84, that's our 160 peak, and 161.84, that's our 162 peak. and the relative sizes, they're not exactly 1 to 2 to 1, but they're pretty close. So 1 to 2 to 1, pretty close. How do you interpret the data? Pause and see what you can conclude about bromine. Okay, we want to think about the isotopes of bromine, the atoms of bromine. If we're seeing 3 peaks in the spectrum for Br2, and the peaks have these abundances, what does that tell us about the number of isotopes and the relative masses of the isotopes of Br, of bromine? Okay, if you think of bromine Br, and let's suppose that there was only one isotope of bromine, so just Br. If there's only one isotope of bromine, then there would be one type of bromine molecule, Br2 with 2 identical atoms. If there were only one type of Br2, then in the spectrum we would see only one peak. So the fact that we see more than one peak means there must be more than one isotope of bromine. Well, suppose there were 2 isotopes of bromine. So this time, let's say there was a bromine, a lighter isotope, I'll say BRL, and there's a heavier isotope, BRH. How many kinds of bromine molecules could you make, Br2, if you had 2 different isotopes of bromine, a lighter one and a heavier one? Pause the video and see if you can figure that out. How many different kinds of Br2 molecules could you make? Well, we've got one type here, BRL and BRH. One way to look at this, for those of you who've done biology or maybe some probability theory, would be to make what's called a Punnett square. BRL and BRH, the light and heavy, and I'll draw a little table like this, and another bromine light and another bromine heavy. Okay, now how many kinds of bromine molecules could we get here? Well, we could get one with 2 bromine light particles. We can get one with 2 bromine heavy particles. But notice that there are 2 different ways to get a bromine light with a bromine heavy. So in the end, looking at this, there are 3 types of Br2 if there are 2 isotopes of bromine, a light one and a heavy one. And not only that, but look at their relative abundances. The amount of the light isotope, the light Br2 and the heavy Br2, there's only 1 each of those, but there's 2 of the mixed ones, the heavy light, there's 2 of those. So we would expect a ratio of 1 to 2 to 1, which is what we see in the spectrum. So looking back here at the spectrum, this first peak, the lightest peak, must be the 2 light isotopes of bromine. This heavier peak must be the 2 heavier bromine atoms, and this one in the middle must be the heavy one with the light one attached. So that's pretty cool, that makes sense. Can we actually tell now what the masses were of the 2 isotopes? Well, we've got the mass of each bromine molecule, and we know that 157.84 was the mass of Br2 involving 2 light particles. So if we take 157.84 and divide by 2, we get 78.92 AMUs. That's the mass of the bromine light particle. If we take the heavier one, 161.84, it has to be the 2 heavy particles. So if we take 161.84 and divide it by 2, we would get 161.84 divided by 2, 0.92 AMUs is the bromine heavy. Okay? Now, could we go even further? Could we say what the abundances were for the two isotopes? We know the abundances of the molecules. Could we actually figure out the abundances of the two isotopes? I'll stop there and let you see if you could figure that out.